So this presentation deals with numerical integration. We know that integral of the equation y is some function of x within the limits a to b is equal to area under the curve. For numerical integration, we will be learning two methods: trapezoidal rule and Simpson's one-third rule. Trapezoidal rule. In this method, area under the curve is approximated using one or more trapezoidal segments or trapezoidal strips. If we apply a single segment application, that will yield very approximate results. Increasing number of strips improves the result. We'll see how this works. So let us consider the curve which is shown here. So if we shade the area under the curve like it is shown here, we get the actual area. So this is the actual area. So if we try to calculate this area using trapezoidal rule, we will have to consider a strip starting from x equal to a, this point, x equal to a is this point, to x equal to b. This is limit of integration. So this strip will have this area. So if we consider this strip, this height is equal to this height, and this height is equal to this height. The trapezoid gives us area, but this area is very approximate. If you look at actual area and the area given by trapezoidal rule, then we can see that there is a lot of error. So the error is shown here. So this is the actual error. So this is the area missed by trapezoidal rule, and this is the excess area considered by trapezoidal rule. So this way, single application or single strip application of trapezoidal rule results in a very approximate solution. But still, this is some sort of solution. So if we try to calculate area, then that area can be given, or area is given by equation like this. So using trapezoidal rule, area under curve is equal to area of trapezoid, which is equal to average height into width of trapezoid, which is equal to f of a plus f of b by 2, that is average height, into width of trapezoid, that is b minus a. So a, b are limits of integration. Now let us study multiple strip application of trapezoidal rule. We can improve accuracy by using multiple trapezoidal strips. How this happens is shown in this figure. So let us say this is the single strip application. So if we apply a single strip, then the area given by trapezoidal rule is this much. This is the area given by trapezoidal rule, and this part shows the error. If I consider two strips, then in that case the area that is given is equal to this much. This is the area given by first strip, and this is the area given by second strip. So if we total this area, then we get area of the curve, and we can see that the error in this case is much smaller than error in this case. So single strip application produces a lot of error, whereas two strips can reduce error margin by a lot. So this naturally means if you consider 4 strips, the error will further reduce, and 8 strips will reduce the error further. So multiple applications of trapezoidal rule results in more and more precise result, but there has to be some limit. So we can apply multiple strips, but there has to be some limit, because the benefits of number of strips goes on decreasing gradually. For example, you can see here that one strip application and two strip application. If you compare these two applications, then two strip application has reduced error by a very good margin, but the error reduced by 4 strips will be smaller compared to the error reduced by 2 strips. So as number of strips goes on increasing, the result improvement goes on decreasing, or improvement in the result goes on decreasing. So we have to stop somewhere. So we have to, you can say, limit somewhere. So this slide shows the actual application of trapezoidal rule, which is multiple strip application of trapezoidal rule. So this figure shows how we can fit multiple strips, strip number 1, strip number 2, strip number 3, and so on. So multiple strips to a curve. Area of individual strips can be calculated, and that can be added to get area under the curve. So this process can be shown using formula is like this. So this formula is area under the curve is equal to h by 2. What is h? H is width of one strip, which is equal to b minus a divided by n. For example, this is h, width of single strip. All strips are of equal width, and therefore h is width of any one strip. So h by 2 into f of x0, where f of x0 is value of y at x equal to a. So f of x0 is basically f of a. So a and b is limit of integration, a and b. So f of x0 is f of a, f of xn is f of b, or value of y at x equal to b. F of xi are values of y at intermediate points. H, as we have already seen, is width of one strip, and n is number of strips. So if this is the case, then we get this formula: area under the curve is equal to h by 2 into f of x0 plus 2 times summation of f of xi, where I varies from 1 to n minus 1, and then f of xn, which is f of b. So f of a plus f of b. F of a is y at x equal to a, this is y at x equal to b, and these are values of y at intermediate points. So this is f of a, this value of y is f of a, this value of y is f of b, and this is f of x1, f of x2, f of x3, and so on. So this is the equation for area. Using this equation, we can calculate area under the curve using trapezoidal rule. So let us try to understand the solution using trapezoidal rule using a problem. So the problem is calculate area under curve y is equal to 1.2x square plus 2x within the limits x equal to 0.25. So the value of a is 2.5 to x equal to 5. So limits of integration are x equal to 2.5 to x equal to 5. So 2.5 is value of a, 5 is value of b. Using 10 segments. So number of segments is also specified. So if this is the given problem, then we can try to solve the problem using trapezoidal rule. So we can try to solve the problem manually using Excel. So for this, the data required is value of a, which is 2.5, value of b given is 5, and is number of strips, which is given as 10. Width of each strip will be equal to b minus a divided by n. So 5 minus 2.5 divided by 10, which is equal to 0.25. So this is the data which is either given or we have just calculated. Now using this data, we can try to calculate the area under curve using either a program or using Excel. So next slide will show a solution using Excel or a spreadsheet software. So the solution shown on the next slide is in tabular form, so this is basically Excel form. The third column shows m, which is the multiplier. So what is the multiplier? Multiplier is the value by which the terms of f of x are multiplied. So if you remember the equation, you should remember the values of y or values of f of x were multiplied by 2, except for first and last value. So we have seen earlier that except for the first and last term, all values of y, that is f of x, were multiplied by 2. So this has been taken care of by using m, or a separate column for m, where value of m is equal to 2 for all strips except first and last strip. So this sheet or this slide shows solution using Excel. So here we have shown various columns. This is the point number column. This column shows values of x. This shows values of m, which is the multiplier, which is 1 for first strip, 1 for last strip, first point and last point. And for intermediate points, the value of m is 2. If you remember the equation is f of x0 plus f of xn plus 2 times f of xi. So 2 times this plus 2 times this plus 2 times this and so on. This whole thing multiplied by h by 2 gives us area under the curve. So that has been solved here. So here we have calculated individual values of x. This is the multiplier. This shows values of f of x, that is values of y, where the equation is given. These values of y are multiplied by multiplier m, and we get the values of m into f of x. These values are shown here. Sum of these values is shown here. This sum multiplied by h by 2 gives us area under the curve, which is shown here. That is 62.53 units. So this flowchart shows us how to calculate area under curve using trapezoidal uses a program. So the first part is inputting data. So here we have accepted value of a, b, that is these are the limits of integration, and this is the number of strips. So assuming this as the given data and the given equation. For example, here the given equation is y is equal to 3.12 x cube plus 1.54 x square minus 6.23. So if we want to calculate area under the curve using this equation, area under this curve within the limits a to b using these many number of strips, then this is the flowchart. So this flowchart shows a function, and this is the flowchart for main program. So the first step is reading data, value of a, b and number of strips. Here we have calculated width of one strip, which is equal to b minus a divided by number of strips. Then here we have called this function. This function has been called for x equal to a and x equal to b. So the value of f at x equal to a, that is f of a, plus f of b have been summed, and these have been stored temporarily as area of the curve. So at this stage this answer is not correct, but this is the intermediate value. After this we can go on adding values of f of x multiplied by 2 in this value of area. So that way here we have implemented a do loop. Value of x varies from a plus h to b minus h. Why this is the case? Because we have already considered f of a and f of b. So if we skip those values, then the first value of x is a plus h and the last value of x is b minus h, and the step size is h. So x varies from a plus h to b minus h with a step size of h. Here we get values of f of x. We multiply that by 2 and add it to area. So this way we get the next approximation of area. So at this stage area is equal to f of a plus f of b plus 2 times f of xi. Now this whole thing will be multiplied by h by 2 to get the area. So area has now been calculated finally here. So area is equal to the previous value of area, which we have calculated here, multiplied by h by 2, and then that has been displayed here. So this program calculates area under curve using trapezoidal. So this program implements the flowchart we have seen on earlier slide. So this is the equation. F of x is equal to 3.12 x cube plus 1.54 x square minus 6.23. So data that is required to be given by user is value of A, value of B and number of strips. Using this data, we have calculated the strip size here, B minus A divided by NS, and this part calculates area under the curve using trapezoidal rule. So this is the first calculation, that is the intermediate calculation, f of A plus f of B. To this we add 2 times f of x, where x varies from A plus h to B minus h. Then to this whole value we multiply by h by 2, which gives us area under curve using trapezoidal rule. Here we have finally displayed the answer. So this is the value of area that is calculated. So this way we get area under curve using trapezoidal rule. This slide shows the Simpson's one-third rule. Application of Simpson's one-third rule for calculation of area under the curve. Simpson's one-third rule is an improvement over trapezoidal rule because it gives slightly better results. It uses a parabola connecting 3 equally spaced points to estimate area under the curve. So instead of a trapezoid, we use a parabola in this case. So this diagram or this part of diagram shows the actual area. This diagram shows area estimated by Simpson's one-third rule, and this shows the error. This also means that there is always an error involved when we use the numerical integration technique, but the error can be reduced by multiple applications of the strips. So using Simpson's one-third rule for a single segment application, this is the equation. Single segment application is not preferred because the results are very approximate. Multiple application of Simpson's one-third rule improves the result. Accuracy of estimate can be improved by dividing the interval into multiple segments, as in case of trapezoidal rule. So for multiple segment application, this is the equation. So equation for calculating area under curve using Simpson's one-third rule is equal to h by 3 multiplied by f of x0, that is f of A, plus 4 times f of xi, where I varies from 1 to n minus 1. So values are I are 1, 3, 5 and so on up to n minus 1, that is the last breaking point, plus 2 times f of xj, where j varies from 2 to n minus 2. So values of j are 2, 4, 6 and so on, plus f of xn. So as in previous case, f of A plus f of b plus 4 times f of xn plus 2 times f of xj. This is what the equation is, and this whole thing is to be multiplied by h by 3. So f of xi and f of xj are intermediate points. So these are basically alternate points. So first point is f of f of A. Next point will be f of xi. Next point will be f of xj. Next point f of xi. Next f of xj. F of xi. F of xj. This will be continued till last broken point. Last broken point will be f of xi, and the last point will be f of b. For this to happen, the number of strips must be an even number. The numbering starts with 0. This problem is used for understanding the application of Simpson's one-third rule for calculation of area under the curve. So assuming y is equal to 1.2x square plus 2x, we can try to integrate the equation within limits x equal to 2.5 to 5 using 10 segments. As in the previous case, the next slide shows the manual calculation or calculations using Excel, and the next slide shows flowchart, and next slide will show the program. This is the implementation of Simpson's one-third rule using Excel or some spreadsheet software. So these are the point numbers. First point is number 0, 1, 2, 3 and so on. So this is these are values of xi. I equal to 1, then I equal to 3. Next value of I is 3. Next value of I is 5, 7, 9. So this is the last but one point. So n minus 1th point. Whereas values of j are 2, 4, 6 and 8. F of x at j equal to 2, 4, 6 up to n minus 2. So this is n minus 1, n minus 2 points. So alternate points are to be considered as point I and point j. Point under I are to be multiplied by 4, whereas points under j are multiplied by 2. These are values of x. So this column shows values of x. This is the multiplier column. Multiplier for first value is 1, last value is 1. Ith values are multiplier 4 and jth values are for multiplier 2. So these are values of f of x and these are values of m into f of x. Summation of all these values gives us this value, and this multiplied by h by 3 gives us area under the curve, which is same as in case of trapezoidal. So this flowchart shows the application of Simpson's one-third rule. So here we'll read data. This step for calculation of h. This is the first step, intermediate calculation of area, f of a plus f of b. F of xi calculation is done in this flow. So first value of x at I equal to 1 is given by a plus h, and last value is b minus h, and values of x increment by 2 times h. So x varies from a plus h to b minus h, and the increment is 2h. All the values of f of x, that is values of y, are multiplied by 4 and added to area. So next rule shows values of j. So value of first value of x is a plus 2 times h, and the last value is b minus 2 times h, and again the increment is 2h. So these values are multiplied by the multiplier 2 and added to area. This whole thing is multiplied by h by 3 to give us value of area. This value is displayed here. This slide shows the program, which is basically implementation of the flowchart shown on the previous slide. So this is the equation, which is used in the form of function, a statement function. Here we read values of a and b. Here we read ns. Ns is number of steps. So here we have added additional part, which is not there in flowchart. So here what we have to remember is value of ns has to be even number. So if ns is even, then only program is allowed to continue, otherwise program is terminated. So to check whether the value is even or not, what we do, we want to divide ns by 2 and again multiply it by 2. If we get back same number, then that means ns is even. But if it is not equal, then it means it is odd. In that case, we stop the program execution. So we display this message: number of steps must be a even number, and then we terminate the program using stop statement. Otherwise, the program continues. That is, if value of ns is even, then the program will move to this step, that is calculation of h. After this, we will calculate area using this equation, this loop, and the second loop. After this, the value of area will be multiplied by 8 by 3 to get the final value of area, which will be displayed, which is displayed here. So this is how the program works.